This last bit of the binomial theorem is where we actually look at some of the patterns and relationships that exist between all the different coefficients. But pretty much every question starts with the binomial theorem. So that's your starting point, is to say, okay, well, this is the binomial theorem. How can I use it to solve this problem? So a reminder, binomial theorem, in sum notation, NCK, x to the k is the general term, and then we have all the terms from k equals 0 to n. And if we were to expand that out, we'll get NC0, NC1x, NC2x squared, and so on and so on. In the middle somewhere, we put the general term and the last one, NCN, x to the n. Some people find it easier to work with the expanded form when they're trying to do the relationships that we're about to do. Some people prefer to just work with the sum notation. First one, find the values of NCK from 1 to n. Right, I said everything starts with the binomial theorem. So there's the binomial theorem. We have a look at what we're trying to prove. We have a look at what we've got. I'm leaving it in sum notation. Tell me things you see that are different. K equals 1 over here, but k equals 0 over here. That's all right, because if we're dealing with the sums, I can subtract the one that says for k equals 0, and then that will make the sum 1 to n. So I can fix that difference up. What else do you see different? The x to the power of k. The one on the left-hand side doesn't have, over here, the question doesn't have x to the power of k. Ours does. How can we make those the same? You are correct. If you make x equal 1, because of course 1 to the power of anything is 1. All right. Let's let x equal 1, but that means on the left-hand side it'll be 1 as well. But as noticed, this one goes from 0 to n. So 2 to the power of n would be the value of every single coefficient. That in itself is handy to know sometimes too. So that all the coefficients add up to 2 to the power of n. But that's not the question we're doing. We need to subtract that first term. So I'm rewriting the sum as k equals 1 to n, but then just adding NC0, the term where k equals 0. And then that's what I'll move to the other side. But NC0, we don't need to know what n is for that one, because we know Pascal's triangle always starts and ends with 1. So NC0 is 1, so we get 2 to the power of n minus 1 as a value for that one. Okay. This time I haven't written in sum notation. It just wants the sum of all the odd ones. All the odd ones. All right, well, there's the binomial theorem. That's where we're going to start. How is it different? Well, this time I only want the odd ones. So I don't want k equals 0. I don't want k equals 2. I don't want k equals 4 and so on and so on. So if I just write it all out to try and make it a little bit more obvious. So the even ones are all missing. Again, we could do that trick of making x equals 1, but that actually is a better substitution for this one. Instead of 1. What do you think? Minus 1 will be better, because when we make it minus 1, all the even ones will be positive, all the odd ones will be negative. So I'll be able to sort of distinguish between the odds and the evens. 1 minus 1, of course, is, yes, it wasn't a trick question, 0. But what we've got is some simultaneous equations. So if I only want the odd ones, what have I got to do? Add or subtract these to get rid of the even ones. I'll need to subtract. If I subtract them, then I'll get 2 to the power of n is 2 lots of NC1, 2 lots of NC3, and so on. Well, divide both sides by 2, and I've got 2 to the power of n minus 1. There's our answer. Of course, there could have been a very similar question where they asked me for all the even ones. I'd do it exactly the same, but then I'd add the 2 together, and then all the odd ones would disappear. Ooh. K equals 1 to n of k times NCK. All right, there's our binomial theorem. Again, we're going from 1 to n, but we know how to solve that problem. That's not an issue. X to the k, but I'm going to be left with k. How do I turn x to the power of k into k for every single term? You're dead right. Because if we differentiate, the x to the power of k will become k times x to the power of k minus 1. And then we can substitute x equals 1, and we're just left with k. So it's a good idea. Let's differentiate both sides. So on the left-hand side, bring down the power, lower the power, diff the inside, well, the inside's just 1. The right-hand side, we're saying, well, every term we're going to differentiate, so k comes out the front, the power becomes k minus 1. Let x equals 1, and we're almost there. Our sum is k equals 0 to n. So I can break that up. And actually, that term we're getting rid of is going to be 0 anyway, because it's k times. Well, if that term k is 0, it's not actually there. So left-hand side, we had n times 2 to the power of n minus 1. There's our answer. Let's try another. Binomial theorem. Okay, what do we got this time? Instead of the x to the k, I've got negative 1 to the power of k over k plus 1. So I want to turn x to the k into negative 1 to the power of k over k plus 1. Well, I think our substitution is probably obvious. I mean, x to the k, we want to get minus 1 to the k. Well, x equals negative 1 will do that. But we've now got this k plus 1 on the bottom of the fraction. How can we change and get this to k plus 1 on the bottom? Integrate. What a good idea. However, it does introduce another issue, because of course when we integrate, we add a constant. Never forget the constant. So we've got a couple of things we've got to work out. We've got to work out what the constant is. And well, we already know what we're going to substitute in. We want negative 1. So let's see what happens. If I substitute in x equals 0, and the reason I've chosen 0 is because I know what the sum will be. Because if every term is 0 to the power of something, I'm going to get 0. So the whole sum on the right-hand side must equal 0. Well, this will allow me to work out what the constant is. So over here on the left-hand side, we have 1 plus 0 to the n plus 1 on n plus 1. Well, 1 to the power of n plus 1 is just 1. Move it to the other side. There's our constant. It's negative 1 on n plus 1. Okay, so now we'll let x equals negative 1. That seems the logical thing to do, and we're very close. On the left-hand side, we have 1 minus 1, which is 0. But on the right-hand side, wow, so close. What's different? Yeah, look at the power. Question's got k. We've got k plus 1. That's right, it's negative 1. So I could divide both sides by negative 1 and get that back to being negative 1 to the power of k. And so the result we're looking for will be positive 1 on n plus 1. Save the best to last. This is one where what we're going to do is start with an identity which we know has to be true. And clearly 1 plus x to the power of n times 1 plus x to the power of n is 1 plus x to the power of 2n. I mean, there's no questions there. And we're going to compare the coefficients of x to the power of n on both sides and end up with this result. So you would imagine that one side is the coefficient of x to the n on one side and one side is the other. So let's see what happens. There's the binomial theorem. That's what we're going to be playing with. Now we know if we were to expand it all out, there's the expression that I would eventually get. Now I've added in a few middle terms there, and you'll see why in a second. Because we're going to find the coefficient of x to the n in 1 plus x to the n times 1 plus x to the n. All right, so we have to, I've got this expression. I'm going to multiply it by itself. So NC0 has to be multiplied by one of these lovely terms to come up with something x to the power of n. Which one do you think it might be? Yes, would be times NC and x to the n. Now, the NC1x would be multiplied by which one? Now you know why I wrote these last two terms, because guess what I'm now going to say? NC2x squared would have to be multiplied by, and so on and so on and so on. Okay, so NC0, you'll notice I'm using the other notation just to match their question. So rather than writing NCK, I'm using the brackets or parentheses there. So we'd end up with NC0 times NCN x to the n. So you get NC1x times NCN minus 1. And we'd keep doing that all the way along, and then eventually we'd end up with all these pairs. But they're all x to the n. Well, I'm only interested in the coefficient. So we've got NC0 times NCN, NC1 times NCN minus 1, NC2 times NC2, and so on and so on and so on and so on. And we get to the last one, which is NCN times NC0. However, we have a little rule which says the triangle is symmetric. So NC0 is equal to NCN, and NC1 is equal to NCN minus 1. So I could rewrite that as NC0 squared, NC1 squared, NC2 squared, and so on and so on and so on, because they're all matched up with the other one that it's equal to. So it's like multiplying by itself. Okay, that's one side of what we're trying to prove. So we now have the sum of k equals 0 to n of NCK all squared. The right-hand side. 1 plus x to the power of not n, but 2n. So we would expand that out, but somewhere in the middle, there would be a term that goes 2NCN x to the power of n. And it would be the only term in the whole expression that is x to the power of n. So on the right-hand side, the coefficient is that one right there, 2NCN. Ooh, not quite what they've asked us to prove, because if you have a look at the original question, it was actually in factorial notation. So we now know that that sum is equal to 2NCN. Well, let's break it into factorials. That'll be 2n factorial on n factorial. But of course, another way of writing n factorial is n factorial squared. And we have our proof. Right. So 5F, also in that handout, I put in, I think, a couple of worksheets in there, which you might find handy to work through to get the the idea of this style of question.